Let me tell you something that's going to bother you. The name black hole is possibly the worst piece of branding in the entire history of physics. It's worse than misleading. It's a catastrophic failure of language that has infected the mind of everyone who's ever heard the term. When you hear the word hole, what do you think of? An empty space, a void, a drain in a bathtub, a well you might fall into, something you could pass through and come out the other side. That's the image the name creates, and that image is so fundamentally wrong that it borders on cosmic irony. Because here's the truth that will make your skin crawl. A black hole is not a hole. It is not empty. It is not a void in space. It is the exact opposite of everything that word implies. A black hole is the densest object in the known universe. It is matter compressed beyond any nightmare you could possibly imagine. It is not a drain where space goes away. It is the place where space itself breaks down, collapses, gives up on being space. If you think you fall into a black hole the way you fall into a well, you are profoundly, terrifyingly wrong. You don't fall through space when you approach a black hole. You fall through time itself. Now, I know what you're thinking. That sounds like the kind of mystical nonsense that gets thrown around in bad science documentaries. Time and space swap places. Reality breaks. The laws of physics stop working. It all sounds like metaphor, like poetry, like someone trying to make physics sound more dramatic than it really is. But I'm going to spend the next 20 minutes convincing you that this is not metaphor. This is not exaggeration. This is the literal, mathematical truth about what happens at the edge of a black hole, and once you understand it, you will never think about reality the same way again. Let me start with something Richard Feynman understood better than almost anyone. The problem with physics is not that it's too complicated. The problem is that reality itself is genuinely, authentically strange, and our brains evolved to hunt antelope on the African savanna, not to understand the fabric of space-time. So we give things familiar names like hole, and we think we understand them, but we don't. We can't. Not until we really look at what the mathematics is telling us. So here's what we're going to do. We're going to throw away the name, we're going to throw away your intuitions, and we're going to build up from scratch what a black hole actually is, using an analogy that might actually do justice to the horror of the thing. Imagine you're in a river, not floating in it, but flying above it in a helicopter. The river is flowing beneath you, and far upstream, it's flowing slowly. Gentle current, easy to navigate. But downstream, there's a waterfall, and as the river approaches that waterfall, it starts to speed up. The current gets faster. The water rushes forward with increasing violence. Now here's the key part. Imagine you land your helicopter on the surface of that water and you try to hover in place. Far upstream, no problem. Your helicopter can easily match the speed of the current. You can even fly upstream if you want. But as you get closer to the waterfall, the current gets faster and faster. Eventually, you reach a point where the water is moving so fast that your helicopter, even at maximum thrust, can only just barely keep pace. You're not moving upstream anymore. You're not moving downstream. You're hovering in place relative to the shore, but you're burning fuel at maximum rate just to stay still. Now move 1 meter closer to the waterfall. Just 1 meter. Suddenly, the current is faster than your helicopter can fly. You're trying to go upstream, rotors at full power, but you're being dragged backward toward the waterfall anyway. The current is too strong. You cannot escape. You are going over that waterfall whether you like it or not. That point, that invisible line in the river where the current becomes faster than your maximum speed, that's the event horizon. That's the point of no return. And here's the part that should make your blood run cold. In this analogy, you are not the water. The river is not made of water. The river is space itself. Space is flowing. Space is moving. Space is falling toward the black hole like a river flowing toward a drain. And the event horizon is the point where space itself is falling faster than the speed of light. Think about that. We're not talking about things moving through space. We're talking about space itself moving. And inside the event horizon, space is falling inward faster than light can travel through it. You could be a photon, a particle of light, the fastest thing that can exist in this universe, and it wouldn't matter. You could be flying away from the black hole at the speed of light, and you would still be dragged inward because the space you're in is falling faster than you can move through it. You are swimming upstream in a river that flows faster than you can swim. Now let's talk about what this actually means. Let's talk about what happens to you if you fall toward one of these things. And I want to be very clear about something. There are two stories here. There's the story of what happens to you from your perspective. And there's the story of what happens to you from the perspective of someone watching from far away. These two stories are so different, so incompatible, that for decades physicists argued about which one was real. The answer, which is somehow worse, is that both of them are real. Let's start with the outside observer's story, because it's the simpler of the two. Imagine you're in a spaceship, falling toward a black hole, and I'm watching you from a safe distance with a very good telescope. What do I see? I see you falling. I see you accelerating. I see you getting closer and closer to that invisible boundary we call the event horizon. But here's the thing. I never see you cross it. As you get closer to the horizon, something very strange happens. You start to slow down. From my perspective, watching you from far away, you are moving slower and slower. The light from your ship becomes redder and redder, stretched out by the intense gravity. Your clock, if I could see it, would appear to be ticking slower and slower. And then you stop. You freeze. You're right there at the edge of the horizon, and from my perspective, you never move again. You are frozen in time, forever falling, but never arriving. The light from your ship dims to nothing as the wavelengths stretch to infinity. You fade away like a ghost, but you never cross. You're stuck there forever, frozen at the last instant before the point of no return. That's what I see. That's the story from outside. And for decades, this is what people thought happened. They called them frozen stars, because it looked like the collapse of a star would freeze at the surface, never quite forming what we now call a black hole. But here's the problem. That's not your story. That's not what you experience. From your perspective, something completely different happens. From your perspective, falling toward the black hole, you don't slow down at all. You don't freeze. You don't get stuck. You cross the event horizon in finite time, in seconds or minutes, depending on the size of the black hole, and nothing particularly dramatic happens when you cross it. There's no wall. There's no barrier. There's no sign that says you are now passing the point of no return. The horizon is not a place. It's not a thing. It's just a boundary in space-time, and you cross it as easily as you cross the border between two countries on a highway. One moment you're outside, the next moment you're inside. And you might not even notice exactly when it happened. But here's where things get truly, genuinely nightmarish. The moment you cross that horizon, something changes in the fundamental structure of reality around you. The mathematics of general relativity, Einstein's equations that describe how space-time bends and curves, those equations tell us something absolutely bizarre. Inside the event horizon, roles of time and space swap. Now, I need you to understand what this means, because it's not metaphor. Outside the event horizon, in the normal universe where we live, you have freedom in space. You can move left. You can move right. You can move forward or backward. You have choices about where you go in space, but you don't have freedom in time. You move forward in time at 1 second per second, always, inexorably. You cannot stop moving forward in time. You cannot go backward. Time has a direction, and you are forced to follow it. Inside the event horizon, this reverses. The direction toward the center of the black hole, the radial direction, that stops being a direction in space. It becomes a direction in time. And the thing we call time, that becomes space-like. What this means, and I'm giving this to you straight from the mathematics of the Schwarzschild metric, is that moving toward the center of the black hole stops being a choice. It becomes as inevitable as tomorrow. You can move around, you can spin, you can orient yourself however you want. But you cannot avoid moving toward the center any more than you can avoid moving toward next Tuesday. The singularity at the center of a black hole is not a place. It's not a point in space that you could, in principle, avoid by being clever with your trajectory. The singularity is a moment in your future. It is a time, not a location. And it is coming for you with the same inevitability that next Tuesday comes for you right now. You cannot escape it. You cannot avoid it. You cannot outrun it. Because away from the singularity is not a direction in space anymore. It's the past, and you cannot move into the past. Let me give you another way to think about this, because I can see this is bending your brain, and it should. Imagine you're driving down a highway, and suddenly all the lanes merge. Every possible direction you could turn, every exit, every side road, they all curve and merge into one single path. And that path leads off a cliff. You can slow down, you can speed up, you can swerve within your lane. But every choice you make, every action you take, leads to the same destination. That's what it's like inside the event horizon. Every path through space-time, every possible future, every trajectory you could follow, they all end at the singularity. The singularity is not a wall you hit. It's the moment when your future ends. Now, let's talk about what that moment feels like. Let's talk about the actual physical experience of falling into a black hole, because this is where the mathematics becomes visceral. This is where the abstractions turn into body horror. The key concept here is something called tidal forces, and if you've ever studied orbits or gravity, you've heard of this. The Earth has tidal forces. The moon has tidal forces. They're what cause the ocean tides. They happen because gravity gets weaker with distance, so the part of you closer to a massive object feels slightly more gravitational pull than the part of you that's farther away. For normal objects like Earth or the moon or even the sun, these tidal forces are gentle, barely noticeable. But a black hole is not a normal object. A black hole has the mass of a star compressed into a region of space so small that the differences in gravitational pull across the length of your body become enormous. If you fall feet first into a black hole, your feet are closer to the singularity than your head. Your feet feel more gravitational pull. They want to accelerate faster than your head. And the result is that you are stretched. You are pulled like taffy. Your body elongates. The technical term, and I love that this is the technical term, is spaghettification. Your bones pull apart. Your cells tear. The molecular bonds that hold you together snap one by one as the distance between your feet and your head increases from 2 meters to 3 meters to 10 meters to 100 meters. At the same time, you're being squeezed from the sides, compressed inward because the gravitational pull is toward a single point, so everything gets pulled together laterally as it's pulled apart longitudinally. You become a strand, a fiber. A thin line of atoms stretched across thousands of kilometers, falling toward a singularity that is now only microseconds away in your future. And here's the thing that makes this even worse. For a small black hole, the kind that forms from a collapsed star maybe 10 times the mass of the sun, the tidal forces at the event horizon are already strong enough to rip you apart. You would die before you crossed the boundary. Your body would be shredded into atoms before you even reach the point of no return. But for a supermassive black hole, the kind that sits at the center of galaxies with millions or billions of times the mass of the sun, the event horizon is much, much farther from the singularity. The tidal forces at the horizon are gentle, negligible. You could cross the event horizon of a supermassive black hole and feel nothing. You would be alive, you would be intact, and you would have several hours, maybe even days, to contemplate the fact that you are now in a region of space-time where your death is not just inevitable, but has already happened from the perspective of anyone outside. You are already dead. You just haven't arrived at the moment of your death yet. During those final hours, you would see things that no human eye has ever witnessed. You would be falling through a region called the photon sphere, a shell around the black hole where light itself can orbit. Photons circle the black hole in closed loops, and if you were at just the right distance, looking in just the right direction, you could see the back of your own head. Light from your body would orbit the black hole and come back around to reach your eyes. You would see yourself from behind, a ghost image created by photons taking the long way around through curved space-time. You would see the universe outside the black hole compressed into a shrinking circle behind you, growing brighter and bluer as the light becomes blue-shifted by your fall. You would see the entire future history of the universe play out in fast forward as you watch that circle of light. You would see stars born and die. You would see galaxies collide. You would see everything that will ever happen in the universe outside, compressed into the final moments before you reach the singularity, because you are now moving through time faster than the universe outside. And then you would reach the singularity, and at that moment, everything we know about physics stops working. The equations of general relativity produce infinities. The curvature of space-time becomes infinite. The density becomes infinite. Time ends. Not metaphorically, not philosophically. The mathematical structure that represents time ceases to exist. The concept of after this moment stops having meaning. You have reached the edge of the map. Here be, dragons. This is where the story ends. Now, Here's where we need to talk about something that bothered Feynman, that bothered Hawking, that bothers every physicist who thinks carefully about black holes. There's a paradox here, a deep, troubling paradox that cuts to the heart of what physics is supposed to do. Physics is supposed to conserve information. That's one of the fundamental principles of quantum mechanics. Information cannot be created or destroyed. If you know the exact state of a system right now, the laws of physics should, in principle, allow you to calculate what it was in the past and what it will be in the future. Information is preserved. But what happens to the information that falls into a black hole? You, your body, your memories, the exact configuration of every atom that makes you, you, all of that information crosses the event horizon. And from the perspective of the outside universe, it's gone. It's been removed from reality. It cannot be accessed, it cannot be measured, it cannot be recovered, even if the black hole evaporates. And Stephen Hawking showed us that black holes do evaporate over enormous time scales through a process now called Hawking radiation. That radiation is thermal, it's random. It doesn't carry information about what fell in. The information appears to be destroyed. This is the black hole information paradox, and it has been tearing at the foundations of theoretical physics for 50 years. Feynman knew about this problem. He worried about it. Because if black holes destroy information, then quantum mechanics is wrong. The fundamental laws of physics that govern the behavior of particles and fields, they break down. Reality becomes unpredictable in a way that goes beyond mere chaos. The universe stops being a deterministic system. Or, and this is the alternative that's somehow worse, general relativity is wrong. The event horizon is not what we think it is. The singularity is not what we think it is. Something happens at the quantum scale, something we don't understand yet, that prevents information from being truly lost. Maybe there's no singularity at all. Maybe the center of a black hole is something else entirely, something that preserves information in a form we haven't imagined yet. Maybe the event horizon is covered with a hologram of quantum information, a firewall that burns away anything that tries to cross it. Maybe space-time itself is not fundamental, but emerges from something deeper, and black holes are the place where that deeper structure becomes visible. The truth is, we don't know, and that's terrifying, because black holes are real. They exist. We've photographed them. We've detected the gravitational waves they produce when they collide. We've watched stars orbit around them. They are not speculation. They are not theory in the colloquial sense. They are physical objects in our universe, and they represent regions of space-time where our best theories of physics produce contradictions. A black hole is a tear in the fabric of reality. It is the place where the story breaks down. It is where the laws we trust, the equations we use to predict everything from the motion of planets to the behavior of atoms, those laws reach their limit and say we cannot go further. The universe has edges, not edges in space, because the universe might be infinite in space, but edges in knowledge, boundaries past which our understanding does not extend. And black holes sit exactly on those boundaries, daring us to look deeper. And here's the final thought I want to leave you with, the one that kept Feynman up at night, the one that should bother you every time you look up at the sky. Those edges are not far away. They're not theoretical. There is a supermassive black hole at the center of our galaxy right now, 4 million times the mass of the Sun, 26,000 light years from Earth. It sits there in the constellation Sagittarius, invisible, inevitable, a wound in space-time that we orbit around like water circling a drain. And it's not alone. Current estimates suggest there are 40 million stellar mass black holes in our galaxy alone. 40 million tears in the fabric of space. 40 million places where physics breaks and information dies and the future becomes the past. And in the universe as a whole, there might be 40 quintillion of them. That's 40 followed by 18 zeros. 40 quintillion places where reality ends. We live in a universe that contains within itself the seeds of its own incomprehensibility. We live in a universe where matter can collapse so far, compress so completely, that it tears a hole in the structure of causality itself. We live in a universe where there are objects so dense, so massive, so gravitationally extreme that they represent the end of knowledge, and we gave them the worst possible name. We called them holes, as if they were empty, as if they were simple, as if they were anything other than the most violent, most extreme, most reality-breaking objects that the laws of physics permit to exist. A black hole is not a hole. It is not a void. It is not an absence. It is the presence of too much mass, too much gravity, too much curvature in space-time. It is the nightmare at the center of Einstein's equations. It is the place where the map of reality stops and someone has written, in careful mathematical notation, "Here there be infinities." And the most terrifying part? We're just beginning to understand them. Every year we learn something new. Every year the paradoxes deepen. Every year the mystery grows larger, not smaller. And somewhere out there in the dark, in the cold silence of space, those singularities wait, patient, inevitable, growing slowly as they consume matter and light and information. Growing until, in some unimaginably distant future, they might be all that remains. Black holes evaporating into a cold, empty universe, the final chapter of a story that began with a bang and ends with darkness. That's the terrifying truth. Not that black holes exist, but that they exist and we don't understand them. Not fully, not yet, and maybe not ever.